5, 4, 3, 2, 1. Liftoff, lifting ICESat-2 on a quest to explore the polar ice sheets of our constantly changing home planet.
The mission of ICESat-2 accurately measure tiny elevation changes on Earth, the height of polar ice, glaciers, and sea level change, all in unprecedented precision and detail. APL-UW Polar Science Center scientists Jamie Morison and Ben Smith are on the science definition team advising the ICESat-2 mission.
When I proposed to be on the science team, it was with the idea of working more on the oceanography that we can do with sea surface heights. There are two reasons for doing that. One is we'd like to know average sea level because we're worried that sea level is rising at about 3 millimeters per year associated with global warming. But the other more day-to-day thing for an oceanographer is that the height of the sea surface basically provides the pressure gradient that drives ocean circulation, so we can estimate currents basically in the upper ocean.
Morison on sea levels, Smith on ice sheet thickness. Both anticipate new data generated by an advanced laser altimeter aboard ICESat-2.
A billionth of a second translate to an elevation change precision of just a few centimeters.
So I did my graduate work on the ICESat-1 satellite. I've used ICESat-1 data to measure how the ice sheets have been changing, and I've been working with that since the early 2000s. It seems very primitive now compared to what we're doing with ICESat-2.
Glaciologist Ben Smith says ICESat-2 will tell us where and how fast ice sheets are thickening and thinning.
We've always had to kind of make bargains with the kind of data that we have. Those compromises kind of go away with ICESat-2. We'll have an instrument that's on all the time, that's making measurements right up to the edge of the ice sheet, that's making measurements with very good spatial resolution. And so we'll start seeing things that we've only been able to dream about so far.
ICESat-2's laser altimeter system, called ATLAS, constantly transmits 6 laser beams to Earth. The photons bounce back from Earth to a telescope aboard the satellite.
You can see the 6 black fibers that are plugged into the back of the telescope. Those actually go out to the detector where they're able to analyze those photons that came back from Earth and compare them to the photons that were sent out to check the stopwatch and see what the distance actually was of that ice that they just measured.
ICESat-2 will be measuring in a footprint every pulse from the laser. There are 10,000 of those per second, and they come down. The satellite is moving at 7 kilometers a second, so we basically get a pulse striking the surface every 70 centimeters, so it's less than a yard. I think it's that resolution that's going to be the new frontier that gets opened up for open ocean oceanography with ICESat-2. And there are other satellites that measure the extent of ice. If you have the extent of ice and you have the average thickness, you can estimate the average volume. And that's really important because in the last 20 years or so, those two combined, the decrease in extent and the decrease in thickness, have reduced the average mass of sea ice in the Arctic Ocean anyway by about a factor of 2.
We'll be able to see the difference in the surface height of Greenland between the end of the winter, when there's as much snow as there's ever going to be there, and the end of the summer when all the melt has happened. So we'll be able to see the magnitude of the summer melt every year that ICESat-2 is up. We'll be able to go into Antarctica and we'll measure small-scale features changing. We'll see water flowing under the ice sheet, seeing lakes inflate and deflate as water moves around under the ice sheet. So there's a whole variety of measurements that are in kind of soft focus now that will be very sharp once we've got ICESat-2 making these measurements.
Liftoff.
Ben and Jamie witnessed the ICESat-2 launch in person.
Seeing the launch was a life-changing experience.
Explore the polar ice sheets of our
It's
constantly
amazing.
changing home planet.
This is to understand how our Earth's changing.
So I was sort of watching this through my kid's eyes, so I brought a 7-year-old and an 11-year-old to see this. And I've been involved in the project for their whole lives. When the rocket actually launched, you could see just how fast it was going. It seemed like it was just gone.
It was almost too fast. Wait, there's got to be more. It just... yeah.
Science at work for you. This is APL, the Applied Physics Laboratory at the University of Washington in Seattle.